All right, welcome back. This is compilations of the practice questions on non-parametrics and probability generating functions. Right. So there are 4 questions here. We're going to look at the first questions now. Right. Okay. Meteorologists claims that the median daily rainfall in London is 2.2 millimeter. A single sample sign test is to be used to test the claim using the following hypothesis. Right? So the null hypothesis stated that a sample comes from the population with a median 2.2, whereby the alternative the state that the sample does not come from populations with median 2.2. Now, in order to carry out this test, 30 sample has been randomly selected, and then observations of the daily rainfall has been collected in London, and then this sample here is compared with 2.2 and given a plus sign if it is greater than 2.2 and negative sign if it's less than 2.2. So here in the remarks there, you may assume that no data values are exactly equal to 2.2. Right? Now the test is will be carried out at the 5% level of significance. So let the number of plus signs be k. All right, plus sign be k. So we need to find in term of k the critical region for the test showing the values of any relevance probability. Right. Now to do that, we are going to use the binomial distributions for this sign test, of course. Okay. Now, in this case, we will label our x to represent. In this case, it actually represent the number of rainfall. Okay, you can say that number of rainfall um, that um, let me see. Let the be k. So therefore, in this case will be we are actually performing a two-tailed test here. So number of rainfalls that is not equal to number of rainfalls. Yeah, number of rainfalls that is greater than 2.2. Right, numbers of rainfall that is greater than 2.2 here. Right. Now this is a binomial distribution. So I'm going to write that down as a binomial distribution that has a number of trials 30, and then we always use that assumptions. Either the rainfalls would be uh, greater than 2.2 or less than 2.2, so the chances will be half here. Right. All right, now we have already set up our binomial distributions. So next we're going to identify whether we are performing a single tail test or a double tail test or two tail test in this case, right? Because the alternative hypothesis stated that the sample does not come from the population with the median 2.2. So therefore, it is a two tail test. Because it's a two tail test, we are trying to identify where is the critical region or where is the rejection region by identifying or evaluate its critical values later on, right? Now, to identify or evaluate its critical values, we need to um, solve this equation here, whereby the probability of x less than or equal to a certain critical value. Okay, because it's a two-tail test, so we have the left-hand side tail must be less than or equal to, because the significant level is 5%, so therefore it must be 2.5% here, or 0.025. Okay, and then the upper tail should be um, more than more than or equal to 2.5% also, right? So I hope that is clear. We're going to start off by analyzing its left-hand tail first. All right, let's look at the left-hand tail. Okay, by using trial and error, by using trial and error, we are going to figure out, like, for instance, for any x less than 20, for instance. Okay, now by using my software here, we can figure that out. So this is uh, um, number of trials is 30, probability of success and failure is 50%. I'm interested to investigate its lower tail. So I'll start off from 20, for instance. Um, okay, less than 20 is too far away. I think that would be less than 10, sorry. Uh, So if you try less than 10, I think less than 10 or 20. Okay, let me change that. So the lower tail, anything less than 10 is suggests that we have, if you use your binomial distributions formula, you should end up with 494, which is approximately 4.9%. Okay, that is much more larger than the 2.5%. So we need to look for another value just to be sure in this case. So 9, for instance. Let's look for 9. If we try 9, okay, okay, we managed to get 0.0214. Okay, now you can see that this is definitely less than 2.5%. Then we are good, right? So we have successfully identified its lower bound. Okay, now we can move on to its upper bound. Because this distribution is symmetrical, so I would start my trial errors from maybe 20. Okay, so I'm going to give it a try for 20. Uh, 20. This is upper bound, sorry. Okay, for 20, I would definitely get 0.0494. Okay, now the main reason why I got the same answer is because the distribution is symmetrical. Okay, and then I can also try x more than 21. Okay, definitely I'm going to get 0.0214. Therefore, this is less than 2.5%. I have successfully determined the upper bound. And then therefore, finally, I can conclude that find in terms of K the critical region. So therefore, the critical region can be written as K less than or equal to, in this case, you can see the lower bound, anything less than 9, and the upper bound, that will be K greater than or equal to um, 21. Okay, now that will give us the critical region to to perform our test or our sign test on. Right. So I hope that is clear. I'll move on to the next question shortly. All right, let's take a look at question 2 here. The heights of 11 randomly selected primary school children are measured. The results in meters are given as follow. Now we need to use Wilcoxon rank sum test at 1% significant level to test whether primary school girls are taller than the primary school boys then, right? Okay. Now, first of all, maybe I would like to label this as the height for the girl, and then this represent the height for boys in this case, right? Okay. Now, the first step in performing the Wilcoxon uh, rank sum test is to actually rank all these numbers here, right? So the first step would be we're going to rank this. So therefore, usually it's best we write down. Okay, so I'm going to write down the rank here. So the girls in this order. Okay, so if I were to, and then the boys will be here. Okay, all right. Now the number of girls in this case, I would actually label this as M here. The smaller sample size I will label as M. Therefore here I have 1, 2, 3, 4, 5. So 5 is the sample size, and then the bigger sample I will label as N. The main reason why I do this is because it's easier to match this variable using the data booklet provided later on, right? MF19. Okay. So from here, I'm going to look at the ranking. Right now in the exam, you have to do it manually then. Let me see which one will be the smallest one. So the smallest one is here. This is rank 1. Okay, so I'm going to write down here first. Rank 1, then you have a 2 here. Oops, I think I did wrongly. That is not rank 1, sorry. I saw it wrongly. This one is rank 1. Yeah, this one is rank 1, 2, and then after that we have a 3, 4. Okay, hold on, let me erase this. This is a 4. That will be a 5. Yeah, and then after that you have a 6. Okay, so this one is a 6, 1, 3, 8, 6, and then after that 7, 8. So this one is 8. Um, After that you have 9, 10, 11. Right. So those are the rank. So therefore I'm going to write down here 8, 3, 11, 6, 9, and 10. Alright, so here I have 7, 5, 4, 2, and 1 here. Right. Therefore, the total the total ranking in this case, okay, uh, you can actually sum up the total ranking here, right? So the total ranking for the smaller sample size, this one usually we can write it down as RM. Then again, the RM that I'm using is also matches the symbol used in the data booklet. So RM is the total rank for the smaller sample. So here we have like a 12, 16, 18, 19. So this part will be a 19 here, right? And then next, I would like to calculate. Okay, so I would like to calculate the test statistics, right? So the test statistics in this case, for the test statistics, I need to calculate this m plus n. Okay, now if you can't remember correctly, you can always refer to the data booklet. How do we actually calculate the test statistics using this formula here, right? So therefore, in this case, we have the m to be 5, 6 plus 1 minus 19 here. So in this case, we have like 11, 12, 6, 60, 41 here, right? So here we have two test statistics here. It's between this rank and these test statistics that we obtained. So what we need to do is that we're going to choose the smaller value between the test statistics that we have calculated here and then the ranking here. Therefore, we are going to write down our test statistics. Okay, maybe I will write down the. So therefore, at this point, we're going to conclude our test statistics as the smaller value between these calculations and the rank itself. So which is 19 here, right? So I hope that is clear at this point. Now, once you are satisfied with this, then we're going to refer to the data booklet. Okay, so I'm going to bring the data booklet here a bit so it's easier to see. All right, now if you have forgotten the formula itself, you can read it directly from the data booklet. It says that the test statistics is the smaller value of the rank and the calculations given here. Right. Okay. So once you're ready with this, all you need to do is just um, identify the significant level. In this case, is 1%. So whether we are performing uh, one tail test or two tail test. Yes, that part I forgot. I forgot to include here. So just let me write it down. I think I spent too much time on calculating this. I forgot to mention my um, because it's a test. So I think the first step you should actually write down your hypothesis test, which I have forgotten here. So the hypothesis test would be in this case the null hypothesis would be the height of girls would be the same as the height for all the primary boys, right? Whereby the alternative hypothesis, based on this, we want to test whether the primary school girls are taller. So we are testing whether the primary school girls is taller than the primary school boys in this case, right? So based on this, okay, and then the alpha. Okay, now the significant level is 1%, or in this case is 0.01 here. Okay, okay. So yeah, I'm going to erase this so that um, it's not very messy, so that I can show you the data booklet here. Okay, let's look at the data booklet. Okay, this is the data booklet here. All right. So in this case, what we are looking for is um, significant level of 1% is a single tail test because this is greater than single tail test. The sample size for n is 6, sample size for m is 5. So you look at m is equal to 5, n is equal to 6. So we look under 6, m is equal to 5, and then it's 1% single tail, one tail test. So that actually gives us 17. Right. So therefore, the critical in this case, the critical value for the W in this case, the critical test statistics is 17. And then we know that our test statistics is much more greater than the critical value. So since it is much more bigger than the critical value, therefore we fail to reject. In this case, we will say that we fail to reject our null hypothesis. Right now, since we fail to reject the null hypothesis, we can conclude that um, the primary school girls are exactly the same height as the primary school boys in this case. Therefore, we can conclude that the height of the schoolgirls would be the same as the height of all the primary school boys, right? Okay, so I hope that is clear for section number 1. I'm going to show you section number 2 shortly. All right, or we can conclude in such a way that knowing that the test statistics is greater than the critical value, we fail to reject H naught. We fail to reject our null hypothesis. We can also conclude that we have insufficient evidence. We have insufficient evidence at 1% significant level to suggest that the primary school girls are taller than the primary school boys. All right, so that's another way to write your conclusion. Instead of saying fail to reject the null hypothesis, Therefore, we can conclude that the primary school girls are having the same height as the primary school boys. I think the better versions to conclude this would be, because we are trying to test whether the primary school girls are taller than the primary school boys, and then we don't have sufficient evidence to suggest that. Therefore, I'm going to write down another conclusions here. Since we failed to reject the null hypothesis, we can no, we don't have sufficient sufficient evidence at 1% significant level um, to suggest or to conclude that to suggest that the primary school girls is actually greater than the height of the primary school girls is actually taller than the height of the primary school boys, right? So that's another way to conclude, right? So I hope that's clear. Right, let's take a look at the second sections of this second question. It is decided to repeat the test using a larger random samples. The heights of 20 girls and 18 boys are measured. All right. Now find the greatest value of test statistics W, which will result in the conclusions that there is an evidence at 1% significance to suggest that the primary school girls are taller than the primary school boys here. Right. So here we know that the sample size for the larger sample, which is the primary school girls, n equal to 20. The for the school boys, we have a sample of 18 here, so we'll label that as n equal to 20, m equal to 18 there. Now, because the sample size is huge in this case, so therefore we no longer can use the Wilcoxon rank sum test table. Instead, okay, you will notice that if you refer to the table itself, the maximum value for m and n can only go up to 10. So if you have any value that is larger than that, the table suggests that for larger value of m and n, the normal distribution should be used. And then we need to calculate the mean, which is given by this expression here. And then we need to calculate the variance, which is given by 1 over 12 mn multiplied by m plus n plus 1 here. Okay, we're going to do that here. Okay. Okay, let's calculate the mean here. So the mean is given by 1 over 2 m m plus n plus 1 here. And then that would actually give us 18. This one will be 18 plus 20 plus 1. And then if you use your calculator, you should obtain 351 in this case, right? And then next we're going to determine its, okay, maybe I'm going to write to the left a bit, okay, so that I have more space to write. So this is m. Okay, that will give me 18. 18 plus 20 plus 1. That would give me 351. Right. And then next, I need to calculate my variance, which is 1 over 12 m n m plus n plus 1 here. Okay, so that should give me 18, 20, and then the same thing, 39 here. Okay, let me see what do I have. This time here, I will have, so let me see here. Okay, I have 1170. So that should be 1170. Okay, all right. Now we are ready. We have a sufficient evidence to suggest that at 1% significant level, the primary school girls are taller than the primary school boys. So therefore, it means that the probability of the ranking that is less than the test, the greatest value of the test statistics must be less than or equal to 0.01 at 1% significant level. And then this equation here is always less than W based on Wilcoxon rank sum test. Now, before we continue further, we are trying to approximate discrete random variable using continuous random distribution. So therefore, we have to perform continuity correction. So by performing continuity correction, we need to, oh yeah, I forgot, this is initially it was the greatest value of test statistics should be less than or equal to. Now, after performing a continuity correction, that should be W plus 0.5. Okay, so I hope that's clear at this point. All right. Now from here, we're going to convert that to z-score. Okay, so 351 over 1170 square root. All right. Now next, we're going to refer to our data booklet one more time in this case. Okay. Now this time we are no longer going to refer to the Wilcoxon rank sum test table, but instead we're going to refer to our normal distributions table now. Okay, not the t-test, but the normal distributions. All right, so we have normal distribution here. What we are interested to get is this is 1%. So based on this table here, this region is 1%. The shaded region should be 99%. Therefore, I'm supposed to look for this section here for 99%. Therefore, that would give me a 2.326 then. 2.326 as my z-score, right? So I hope that's clear. I'm going to use that z-score now. Okay. Therefore, I can write this result W plus 0.5 minus 351 divided by 1170 square root here. Now, in order for us to have sufficient evidence to reject the null, therefore, this z-score must be less than 2.326, and then it should be negative here. The main reason is because if you refer to your normal distributions, okay, sorry about that. What a lousy drawing there. Okay, if you refer to your normal distributions, now this region should be 1%. This region should be 1% here, right? And then your z-score started off from 0 here. So therefore, this value must be negative 2.326. Yeah, must be negative 2.326. That's the reason why this must be less than negative 2.326 for us to have sufficient evidence to suggest that the primary school girls' height is taller than the primary school boys here, right? Okay, so from here, all we need to do is just solve this. So therefore, that will be 350.5 less than negative 2.326 square root. All right, so let me try this out. 1170, is it 1170? Yep, correct. And then we need to 326. Yep. Okay, and then after that we need to, okay, so we have W less than 270.9 there. Therefore, the maximum or the greatest value of the test statistics, because this is less than this, should be 270. Now that will be our greatest value of the test statistics. To provide us with sufficient evidence at 1% significant level to suggest that the primary school girls is taller than the primary school boys there. Right. So I hope that is clear for this question. Right. All right. Question 3. Okay. Now the discrete random variable x is given as such. Now this one is basically looks very similar like the geometric distribution. Okay. Now show that the probability generating functions of x given as mx can be written in this form here. Right. Now then after that we're going to find the range of values of t for which the formula of the probability generating functions in part 1 is valid. And then therefore the last part we're going to use the probability generating functions to obtain the expected value for x and the variance for x. All right, let's get started. Number one, okay. Now as usual, I'm going to use the definitions for the probability generating functions. So mx in this case is given by the expected tx. Okay, right. That is basically the same as px here. Okay, that is from um, x equal to 0. I would say until infinity based on this description here. All right. Now I'm going to substitute all its discrete values that we can obtain from here. So therefore, these probability generating functions can be written as, okay, so we start off from t to a power of 0. So t to a power of 0 multiply with its probability. So when x is equal to 0, that is 3 over 4. Okay, 1 over 4 to the power of 0. And then we're going to continue further, t1, 1 here, and then t2, and so on and so forth, of course, right? So from here, we try to simplify it and then see whether we can obtain any particular pattern here. So 3, 4, we have 3, 4, 1, 4, t, and so on and so forth here, right? And then furthermore, we can factorize this into this. All right, now we sort of get a pattern, right? Now this indicate that it is a infinite geometric series, okay, which we can obtain its summation using this formula. So I'll write down a remark at the side just to recall the summations of geometric series is given by this is a infinite summation, so therefore it's a over 1 minus r. Now bear in mind we can only obtain these summations provided the magnitude of the common ratio must be less than 1. Now that's a requirement. Okay, so therefore the first term is a 1, 1 minus the common ratio. So the common ratio is this part here. And then by simplifying, we will get 3 over 4 minus t. Okay, so I hope that is clear at this point. Okay, we are done with number 1. Now for the follow-up questions, number 2, as I mentioned before, these summations of geometric series, infinite summations, is only true when the magnitude of the common ratio less than 1. Now the common ratio that we have here is 1 over 4 t. So the magnitude must be less than a 1. Okay, knowing that this is true, we can conclude that the t must be lying between a 4 and a negative 4 for these summations to be valid. Right. Now I hope that is clear. All right. So next I'm going to move on to number 3, how to make use of the probability generating functions to obtain its expected value x and then the variance itself. All right. Okay. So let me clean this up. We're going to move to 3 now. Okay, we don't need this anymore. Number 3. Okay. Okay. Now from here, we can apply the uh, definitions for expected value of x, which is given by the first derivative of, oops, I think they are using m in this case. So the first derivative of the probability generating functions, first derivative, okay, and then by letting the t equal to 0. By letting the t equal to 0 here, right? Now that's the definitions that we're going to make use of. Now to do that, we are going to differentiate our probability generating functions by obtain its first derivative with respect to t. Okay, so that will be, let me see, negative, negative, positive. So that will be a 3 over 4 minus t square here. Okay. Okay, now that will be the first derivative. And then by letting the t, so we let t equal to, so let t equal to 0. Therefore, our first derivative would be equal to 3 over 16. And then we can conclude that, therefore, the expected value for x can be written as here, very obvious, 3 over 16. And then we are done with the first part here, right? So I hope that's clear. Now, second part, variance. Variance of x is given by the definitions of this x square minus of ex square here. All right. Okay. Now that will be our. All right. Now that will be our original definitions in this case. All right. And then by making use of the uh, probability generating functions, we can obtain another definitions for variance. Now I hope that yeah, you guys still remember this. Okay, so that will be equal to, okay, hold on, let me see whether I can remember this. That will be equal to the second derivative of, oops, we are not using g here, we're using m. So the second derivative of this probability generating function, and then we also have the first derivative, and then finally we have this first derivative, a square. That is indirectly from here, right? And then this part was derived from these particular definitions. All right, now just to walk you through again where this definition was derived from. Okay, so now I'm just going to show you a very brief proof how this formula actually came about. All right, so we started off from the definitions for the probability generating function, which is given by this. Okay, so that's what we have. All right. Now from here, we can actually differentiate this with respect to t. Okay, so if you differentiate this with respect to t, now that is, okay, now I forgot to write this. This is basically t x p x equal to x here. It's a summation. So if you try to differentiate this with respect to t, so therefore that will be xt x minus 1. Okay, so that's what we have at this point. Okay, and then after that you can perform the second derivative. So the second derivative basically is just x minus 1 t x minus 2. Okay, now that's what we have, right? All right. Now from here onwards, you can see that this is pretty much the same as e. If I were to expand this, I will get let me see, I will get x squared minus x t x minus 2, tx minus 2, right? Okay, so there you have it. And then by letting your t go to 0, if you let your t go to 0, that is basically just ex squared minus ex. All right. So from here, you will notice that your ex squared is basically the second derivative of the probability generating functions add up with the expected value for x, which is the first derivative of the probability generating function, right? So that's how we obtain this very little section here, right? So I hope that's clear. Now, once we knew this is the relationship, all we need to do is just obtain the second derivative for this. So I'm going to find out the second derivative. So the second derivative for this will be, let me see, that will be negative 6 positive 6. Okay, so that will be 6 over 4 minus t3. Okay, and then by letting the t go to 0, therefore my second derivative would be 66 over 64. Right, and then therefore from here I can conclude that my variant x will be 6 over 64, add up with my expected value, which I got it from here, and then finally I need to subtract off with a square here. All right. Okay, is that correct? Just let me check for a while. Yep, that's correct. Okay, just let me try to tabulate this using my calculator, and then let's see whether I got it correctly. Okay, now that will be 4, 12, 18. 18 over 64. Okay, so 18 over 64. All right, so I have just write it down here. So I think I'll have 18 over 64. Subtract off with a 9 over, let me see. So that is 256 here. Okay, so in order to get 256, I need like 4. So that is 72. So 72, 63. So that will be 63 over 256 then. All right, now that will be my variance in this case, right? So I hope that is clear. I'll move on to the next question shortly. Right, question 4. The discrete random variable y has a probability generating functions given by this function here. Now the first question we need to find out its specific probability at y equal to 3. Then next we're going to find its expected value ey here. Right. Now to recap, all the probability generating functions can be defined based on the definitions. So in this case, since we are dealing with y, So the definitions for probability generating functions, y here is given by this expected value notation, which is ty here. Okay, so you can write down in its expected form, or you can write down in its probability form. Okay, as such, right? So the y, you should start from 0 until n, for instance. Okay, and then, or you can represent it explicitly in this way. Okay, you can represent this explicitly as t to the power of 0, py equal to 0, plus t1 py equal to 1, plus t2 py equal to 2, and t3 py equal to 3, and so on and so forth, of course, right? Until you can say that until tn py equal to n. All right. Now that is the general probability generating functions for any discrete random variable. Right. So to answer the first question here, you will recognize it quite directly. The coefficient attached to T3 is the probability that we are interested to obtain in this case. So all you need to do is just expand this expression, polynomial expression, and then eventually recognize the coefficients attached to T3. That would be the probability for py equal to 3. Okay, now that's how direct it is. Right? Let's take a look at how to work with this. So we are given gy is 1 over 126 negative 1. All right, now that's how it look like. Now, of course, we may like to restructure this properly. This can be written as, okay, if you like, you can actually write it down as 1 over 126t. Nothing much we can deal with this. And then this one is actually 1 over 1 minus t over 2. Okay, now that's how it look like. Now, of course, for me, I prefer to simplify this a bit. Simplify this denominator a bit. So that will be like you can multiply by 2 at the denominator so that you can get rid of the fraction here. So therefore, now in this case, it would be 1 over 126t, 64 minus t6, and then since I multiply 2, it will become 2 minus t then. Okay, now that's how it actually look like. And then of course you notice that you can do a bit of simplification here and there. That is fine. So you can simplify that. Okay, now after simplifying this, we will get something like this. We will get 1 over 63 because these two cancel with this. So therefore you get 64 minus t6, 1 over 2 minus t here. Okay, and then after that we can further simplify this. Okay, we can actually simplify that as, now before that I can write as a to the power 2 uh, t cubed to the power 2. So you will recognize that this is actually a squared minus b squared form. Okay, now that's how it look like, right? So from here, we can further write it down as, I would say, a to the power 3 here, and then 8 minus t3. Okay, all right. And then now you notice that this can be further factorized again if you like. Um, Now, if you don't want to factorize, that is fine. You can expand everything. So if you factorize this, all right, so that's what we have currently. And then from here, we can simplify this. Okay, now of course, I do make a restrictions saying that the t should not be equal to a 2 then in this case, right? So that we can cancel out this. And then therefore, we will end up with this. T, what we have is 8 plus t cubed, and then 4 plus 2t plus t squared here. Okay, and then we are almost done. At this point, all you need to do is just expand this. So if I were to expand this, so there's a t, and then in this case I will have 32, 16t, 8t squared plus 4t cubed. 4t cubed, is it? Yep, correct. And then 2t4, and then finally I have my t5. Okay, now after that you can rewrite again. You can rewrite as 63. Okay, maybe I'll try to write it down in the form that is easier to read. So I'm going to expand everything. That will be t, and then after that you have 1663 t squared, 863 t cubed, and then after that you have 463 t4. What else? We have 263 t5, and then finally we have 1 over 63 t6. Right, these are all the terms that represent the probability generating functions for this discrete random variable. And then, as I mentioned before, all we need to do is just recognize the coefficients that is attached to the T3. So we notice that coefficient attached to T3 is this. Then we can conclude that the probability y equal to 3 is actually equal to 8 over 63 here, right? So I hope that is clear. Now, next I'm going to show you the second methods that we can use to find this probability y equal to 3 using differentiation. Okay, all right. Now I'm going to pause here for a while. I'm going to write down the result that we have here. This is the result that we have. Okay, so I'm going to erase everything. Okay. Do I get that? Okay, hold on. So the result that I have obtained at this point is this. So I'm going to write it down. This gy, the probability generating functions, can be written as this 63t Okay, all right. Now we can actually apply differentiation here. Okay, did I miss out any term here? T2, this is L over T3. I think I missed out a term. Hold on. So this one's supposed to be a T3. Okay, that's T3 L over C3 T3. I have another term. Okay, 433. Okay, I think I accidentally missed that out. Let me try to complete that that will be 4 over 63 T4 plus 2 over 63 T5, 1 over 63 T6. Yeah, okay, there you have it. All right, now the second method, how we can obtain the Py equal to 3 is by using differentiation. So I can actually differentiate this one time. That will give me 3263 plus 3263T. Okay, so that's the first derivative. Then we can apply our second derivative. Okay, so if you apply a second derivative, we will get this. Oops, there's no t here. Okay, okay, so there you have it. And then we're going to move on to the third derivative. Okay, so the third derivative, we will get 48 63. So 48 63, and then we will have 96. Okay, in this case it's 96 63 T plus, what do we have here? We are going to plus 120 63 T square, 120 63 T 3 here. Okay, so that's what we have currently. All right. So how are we going to make use of the result that we have here in order to obtain the result that we intend to get in this case, right? Okay, now I would like you to see here this 48. This 48, this term here was obtained from here, and then this one was obtained from here. Let me see. That is obtained from here, right? You can see that this one was obtained from here, and then this one here was obtained from the derivative of this one here, term 3. So you recognize that that is the derivative of T3 here. Okay, and then okay, now from here all we need to do is recognize what has happened in between here, right? So what happened is that initially it was 8. Okay, in order to get 24, it's actually 8 multiplied with 3. So this one is actually 8 multiplied by 3. Okay, I'm going to write a remark at the side here. You just need to focus on this term. Consider this term for a while. So the coefficient for t square here can be written as 8 times 3 over 63 now for this line. Right, now the next line, this one here, we can write it down as also consider this term here. So that will be 8 times 3 times 2 divided by 63. Right, that's for this line here. And then finally, when we reach this line here, we can get 8 times 3 times 2 times 1 here divided by 63. Okay, all right. And then the last step would be we're going to assign t equal to 0. So assign t equals 0. If you assign t equals 0, basically we are eliminating all these terms here. So if you eliminate all these terms, what is left is only 48 over 63. Yeah, okay. Now at this point you're wondering, how are we going to make use of this result to obtain our P3? All right, now the remark again from here, this is the same as 8 times 3 factorial. You can see that this is 3 factorial over 63 there. Okay, all right. And then you will notice that this term here can be actually written as 3 factorial multiplied by y3. Because we already knew py equal to 3, we already knew from our previous sections py equal to 3 is actually 8 over 63. So typically this result is 3 factorials of py equal to 3. So from here we can conclude that probability y equal to 3 is actually 1 over 3 factorial gy, the third derivative. So the general form that we can use in the exam would be, if you are interested to find y is equal to n, for instance, that can be obtained by using n factorial multiply with the derivative of the probability generating functions to the power of n times, and then by letting your t equal to 0. And then that would allow you to obtain the specific probability that you are interested to obtain here without expansion. All right, let's take a look at the second section. Now, this is the result that we have obtained in our previous question number 1 after we have fully expanded this. Okay, now this is the probability generating functions in all its terms. Okay, now from here, in order to find the expected value for y, we are going to make use of the definitions for expected value here, which is actually given by the first derivative of the probability generating functions, and then by letting your t is actually equal to letting your t equal to 0. Right. Now that's the definitions for getting the expected value for y here. So all we need to do is just differentiate the probability generating functions first time, or getting the first derivative for probability generating function. In this case, we have 32, 63. Okay, so there you have it. And then all you need to do is let t equal to 0. So therefore, our first derivative would be, if you let t equal to 0, all these terms will be 0. Therefore, we only left with this. And then therefore, we can conclude that the expected value for y is basically equal to 32 over 63 here. All right. So I hope that is clear for this question here.